Hi friends, welcome back on our YouTube channel. Today in statistical mechanics we are going to discuss about canonical ensemble. So what is canonical ensemble? We will discuss in our current lecture. So let's start canonical ensemble. In this lecture we will discuss about canonical ensemble. A is an extensive quantity and also A is related to the internal energy and the entropy. So these three topics we will discuss in our current lecture. So first of all, what is canonical ensemble? It is a collection of essentially independent assemblies having the same temperature, volume and number of identical particles. So canonical ensemble is actually the collection of essentially independent assemblies having same temperature, same volume and also the number of identical particles, that is n. To assure that all the assemblies have the same temperature, we could bring all the assemblies in thermal contact with each other. Now, here we are showing canonical ensemble. So, this is our canonical ensemble and these are assemblies and all the assemblies have the same temperature, same volume and also the number of particles, that is n. And these assemblies are separated by rigid, impermeable and dithermic wall. In figure, a canonical ensemble is shown in which all the individual assemblies are separated by rigid, impermeable but dithermic wall. Since energy can be exchanged between the assemblies, therefore they will reach a common temperature. So here exchange of energy is possible between the assemblies. Thus in canonical ensemble, assemblies can exchange energy but not particle. So all the assemblies have the same number of identical particles. Let an isolated system be made up of two subsystems such that H1 and H2 be the Hamiltonian of the subsystem and N1 and N2 be the number of particles in the subsystem. So we consider an isolated system and this isolated system is made up of two subsystems. H1 and H2 be the Hamiltonian of the subsystem. P1 Q1 and P2 Q2 are the linear momentum and coordinates of these subsystems. Also N1 N2 be the number of particles in the subsystems. Also N2 is very much greater than N1, but N1 and N2 are macroscopically large. Now we consider a microcanonical ensemble of the composite system having total energy between E and E plus twice delta E. Also, the energies of the subsystems E1 and E2 satisfy the condition such that E is less than E1 plus E2 is less than E plus twice delta E. So here we consider a microcanonical ensemble of the composite system having total energy lying between E and E plus twice delta E, and the subsystem have the energy E1 and E2. Also the energy of the subsystem satisfy this relation. Since the analysis of microcanonical ensemble shows that only one set of values of E1 bar or E2 bar is important. Now we consider that E2 bar is very much greater than E1 bar. Also, gamma 2 E2 is the volume occupied by system 2 in its own gamma space. So gamma 2 is the volume occupied by the system 2 in its own gamma space. The probability of finding the system 1 in a state within dp1 dq1 of p1 q1 regardless of the state of the system 2 is directly proportional to dp1 dq1 gamma 2 e2. So the probability of finding the system 1 in this state is directly proportional to this one, and it is regardless of the state of system 2. So P1, that is the probability of finding the system 1, is directly proportional to dP1 dQ1 gamma 2 E2, where E2 is equal to E minus E1, because E1 plus E2 equal to E. So here E2 is equal to E minus E1. Therefore, the density in gamma space for system 1 up to a probability constant rho is directly proportional to gamma 2 E2, and rho is a function of P1 Q1. So the density in gamma space for system 1 up to a probability constant is given by this relation. Now, since E2 equal to E minus E1, therefore rho is directly proportional to gamma 2 E minus E1. Since only the values near E1 equal to E1 bar are important and E1 bar is very much less than E2 bar, or E1 bar is very much less than E. So K log gamma 2 E minus E1 is equal to S2 E minus E1 is equal to S2E minus E1 del S2 by del E at E equal to E2 plus and so on. Now del S by del E equal to 1 upon T. So this will be 1 by T. Therefore this relation will be K log gamma 2 E minus E1 is equal to S2E minus E1 by T plus and so on. Here T is the temperature of the larger subsystem. So this temperature is the temperature of the larger subsystem. Now we divide this whole equation by K. So log gamma 2 E minus E1 is equal to S2E upon K minus E1 upon KT. Here K is Boltzmann's constant and S is entropy. Or gamma 2 E minus E1 is equal to exponential S2 by K exponential minus E1 upon KT. Because to remove this natural log, we take exponential on either side. So on taking the exponential here, we get gamma 2 E minus E1, and on taking the exponential here, we get exponential S2 by K exponential minus E1 upon KT. Exponential S2 by K is independent of E1, so it is constant for a small subsystem. So this is constant for a small subsystem. Also E1 equal to H1, and H1 is the function of P1 and Q1. Therefore the ensemble density for a small subsystem, since rho is directly proportional to gamma to E minus E1, and gamma to E minus E1 is this one. It means rho is directly proportional to this one. So rho is directly proportional to exponential minus h upon kt, because this is already constant and E1 equal to H1. So rho is directly proportional to exponential minus h upon kt. Now rho is this one. The ensemble defined by this equation is known as canonical ensemble, and the larger subsystem behaves as a heat reservoir in thermodynamics. So the ensemble defined by this equation is actually canonical ensemble, and the larger subsystem here behaves as a heat reservoir in thermodynamics. The volume in gamma space occupied by the canonical ensemble, that is partition function, Qn is equal to integration d3n p d3n q exponential minus beta h upon h raised to 3n factorial n. So Qn is a function of Vt, and what is this? This is partition function in canonical ensemble. So the volume in gamma space occupied by canonical ensemble is given by this partition function. Here beta equal to 1 upon kt, and k is our Boltzmann's constant. Here this h is equal to dp dq, and this is a constant, and we use it to make Qn dimensionless, because if we solve this relation then we get a dimension h raised to 3n. So to get Qn dimensionless, we divide this equation by h raised to 3n. Also here 1 upon factorial n appears from the rule of correct Boltzmann's counting. So this is from the rule of correct Boltzmann's counting. The thermodynamics of the system can be obtained by Qn is equal to e raised to minus beta a. And what is this a? This is Helmholtz free energy. So here a is a function of V and T, that is volume and temperature, and it is Helmholtz free energy. Now Qn equal to e raised to minus beta a. Now we justify this equation. So justification of this equation. First of all, a is an extensive quantity. Now Qn is given by this relation. From above equation, if the system is made up of two subsystems whose mutual interaction can be neglected, then Qn is a product of two factors, and since h equals to h1 plus h2, so we replace this h by h1 plus h2. Therefore Qn is equal to integration d3n p d3n q e raised to minus beta h1 plus h2 divided by h raised to 3n factorial n. Now e raised to minus beta h1 plus h2 will be e raised to minus beta h1 into e raised to minus beta h2. So this equation will be equal to integration d3n p1 d3n q1 e raised to minus beta h1 upon h raised to 3n factorial n1 into integration d3n p2 d3n q2 e raised to minus beta h2 divided by h raised to 3n factorial n2. And since this is Qn, it means this is our Q1 and this is our Q2. So Q equal to Q1 into Q2. In this way, we can say that A is an extensive quantity. Now, second one is A is related to the internal energy and the entropy as U is equal to ensemble average of H is equal to A plus Ts. Here S is entropy, T is absolute temperature, and A is Helmholtz free energy. Now we prove this relation from identity 1 upon h raised to 3n factorial n integration dp dq e raised to beta a minus h equal to 1. We differentiate this identity on either side with respect to beta. So if we differentiate this identity with respect to beta on either side, then 1 upon h raised to 3n factorial n is constant integration dp dq. Now we differentiate this. So differential of e raised to x is e raised to x. So e raised to beta a minus h. Now we differentiate this with respect to beta. So for it we apply u into v method. So first of all, a minus h is constant and the differential of beta with respect to beta is 1 plus second time beta is constant and we differentiate a minus h, and h does not depend on beta, so its differential will be 0, and differential of a with respect to beta is del a upon del beta at constant volume, and differential of 1 is 0. So on differentiating this equation with respect to beta, we get this relation. Now we transfer this whole here. So a minus h plus beta del a by del beta at constant volume is equal to 0. Now since beta equal to 1 upon kt, so if we differentiate this one, so d beta equal to 1 upon k, and differential of 1 upon t is minus 1 by t square dt. Now we replace this beta by 1 upon kt and this d beta or del beta by minus 1 upon kt square dt. So this equation will be a minus h plus 1 upon kt into del a by del t into minus 1 upon kt square equal to 0. Now k and k will be cancelled out and t is cancelled with this t. So here we have minus t del a by del t. So a minus h minus t del a by del t at constant volume equal to 0. Or u, that is ensemble average of h equal to a minus t del a by del t at constant v. So we transfer this h from here to here. So h equal to a minus t del a by del t at constant volume, and this is our internal energy u. So internal energy u, that is ensemble average of h equal to a minus t del a by del t at constant volume. Other thermodynamic functions can be determined from A by the Maxwell's thermodynamic relation as P equal to minus del A by del V at constant temperature, entropy S equal to minus del A by del T at constant volume, Gibbs potential or Gibbs free energy G equal to A plus PV. So by using this relation we can obtain the value of P. By using this relation we can obtain the value of entropy and Gibbs potential or Gibbs free energy by substituting the value of A and pressure here. So minus del A by del T at constant volume is actually our entropy. So this is our entropy S. Therefore U equal to ensemble average of H equal to A plus Ts. here we end our session. In today's session, we have discussed about canonical ensemble. So, goodbye.